So balance of system components include connectors, cables. I'll talk about mostly today branch connectors, discrete and block fuses. These components have seen limited research examination, but we know there's a quantifiable replacement rate, certainly within the 25-year warranties typically found for PV modules. And how that plays out in older systems remains to be determined. I'll point out that there's presently 2 DOE projects examining the components, frequency of occurrence, and issues like cost associated with BOS components. But yeah, the consequences of degradation and failure include offline modules, strings, and inverters, system shutdown. There's examples from a recent PPRW about the consequences of arc faults and fires. These tend to be more BOS centric and not found in the PV modules, and may have limited publicity, like in the US, for legal reasons. So CAST was developed to work with mini modules, and so we wanted to develop the characterization methods, identify the degradation modes, and be able to distinguish known bad BOS components using CAST. And a couple of specific concerns were to identify the most damaging stressors. This might play out as the use environments, just based on the very different CAST sequences. And then we wanted to know if mechanical perturbation could contribute to failure. And regarding that latter question, it turns out it can very greatly affect the result. So for today, keep an eye for how do we implement this in testing? What are the components that are affected? And then, we're curious also to get some of your feedback about how to further validate the result, but there's certainly concerns that we had in mind. So we were approached by a utility provider, and something like a third of their strings were dropping out, and this was attributed to the branch connectors. Failure here means overheating and softening of components with physical distortion afterwards. There was an overt rise in temperature for certain components in FLIR imaging, with the worst consequences being broken circuits, arcs, and fires. So I give or show some examples of branch connectors for the PV industry here, but the actual make and model that we're studying is going to be confidential, at least relative to this presentation. So the approach here, I'm going to talk about today setting up to examine using CAST. Mike Kempy's working to examine relative to the UL standards. When we started, the number and contribution of the components in the system was not known. So we examined all of the adjoining components in CAST, including the cable connectors, discrete fuses, and branch connectors. And I'll show examples of developing the fixture data acquisition software for benchtop experiments, where typically we're working with a sample each at a time. And that will be evaluated in CAST instead, something like 6 replicates at a time. So the fixture concept that we uses like a push-pull actuation. And we picked this relative to like driving a wedge between the branch connectors. In the installation, these samples have an extent of cable that leads up to them, and so there's quite a bit of degrees of freedom in terms of deflection, maybe rotation too. But the consequence here is that the sample assembly is actually part of the actuation mechanism. We started with a relatively large deflection. In this presentation, we're looking at something like a 1 millimeter actuation, and that's actually been dialed down a little bit for use in CAST. The benchtop version here is run with a DC motor. It looks a bit like an oil well pump once it's running. The CAST version instead uses larger hydraulic actuators. There's a couple different speeds of operation here, depending on the sequence within CAST. So here again is the FLIR image from before. How we ran the test was to start at like either 10 amps or 20 amps and turn up the DC current 1 amp each day until we got the failure. And so what we were seeing was that the static assemblies where we were not perturbing them failed at like 35 amps. And the components are equivalently labeled for 30 amps. And then the dynamic assemblies, these failed at 15 amps, achieving like 130 degrees C in FLIR observation. I don't show it, but the UL connector test, just of the branch connectors, this was running up to close to 38 amps. Much more modest rise in temperature observed there. So the failure modes for the static assembly, this is failing at the fuse element within the discrete fuses in the open circuit. The dynamic assemblies are failing between the fuse and the branch connector. And we suspect that there's some localized arcing going on here. I mean, we observed smoke, local deformation of the plastic. The metal pins were discolored when we pulled these apart, and there was an increased resistance, particularly in the fuse components afterwards. So this shows the LabVIEW run data acquisition for the benchtop experiments. We looked at one measurement per sample assembly, so looking at the static assembly relative to the dynamic assembly. Data has been averaged in 1 minute intervals. We have the option to do a burst mode to get the details of what might be going on at a much faster rate. And yeah, here we compare between static and dynamic, but the Y scale is very different here. We wanted to drive home the point that almost immediately you see an increased variability with the mechanical perturbation. So the experiments here run up to when there's a foldback event, when the voltage rises to a certain limit during current control. We turned that up from 1 second to 25 seconds. A question here is, in the audience, what sort of setting might you use to simulate the inverter operation in your system? Is it fast or slow? We'd like to get some feedback there. So the temperature was also logged per specimen, although it's logged in 4 different locations using discrete T-type thermocouples. This is in a sheet package. So we compare again the static and dynamic sample assemblies. This time the y-axis is the same scale. And yeah, you can see that these are achieving very different temperatures. Now, the FLIR observations indicate hotter temperatures. It's difficult to know in advance the exact hottest location to put the thermocouple, but it is helpful to make these measurements because it gives a sense of when does this start to occur and relatively how are the components affected versus one another. I'll start to get into the failure analysis. This shows the X-ray computed tomography imaging. So we're comparing unaged and aged samples and samples that from the field or from the benchtop experiments. So the field samples show an asymmetry that's not present on the unaged samples. After the accelerated testing, we see a deformation that's not present on an unaged sample. You can ask, well, what sort of temperatures are we achieving here? You can look at the convolute spring component. I'll talk about that coming up. That's composed of copper. The melting temperature of copper is greater than 1,000 degrees. The fuse holders are made of aluminum bronze, so the melting temperature here is like 550 C. And then the solder that's used to attach these is composed of like a tin, silver, possibly copper alloy. And here this is melting at like 220 C. So we're certainly getting that during the accelerated testing. I've shown that some of the non-destructive failure analysis, the X-ray. The next step would be to mill the external plastic. And when we do that, we save the polymer like for examinations. But the goal here is to be able to inspect the metal components, which may show additional degradation that you can or can't see in the XCT. And we're talking about looking using a camera or a microscope for imaging, SEM and EDX, perhaps for composition analysis. And then one of the steps is to unfold the female pin and extract the convolute spring. So this spring helps facilitate the connection between the connector components. We look at it using the same methods as above. Now, one question that comes up is, what's the phase transition temperature and what material is going on if we're getting deformed plastic from our aging? And so we took and did BSC and FTR examination of the unaged samples. This shows the DSC results. We suspected like a hard structural polymer, just handling the samples. On examination, we found a glass transition temperature of like 142 C. This suggests that, this is amorphous polycarbonate. And all the samples we looked at through this range gave a similar response, including the cable connectors, branch connectors, and the ends of discrete fuses. We also compared the same samples in FTIR, and I had a reference polycarbonate sample. We took 2 replicate measurements from each of the samples, and then looked at both ends of the connectors. And so what we're saying here is that we think that black plastic in these components always consists of polycarbonate, most likely stabilized with carbon black. So this now shows some of the additional microscopy. So we're comparing field veiled samples relative to the most recent benchtop sample. And so once the plastic is removed, we see that the metal pins are discolored and that the convolute springs have a distorted appearance. So for the field sample, we see a buckling sort of deformation relative to a less affected spring component. There's also evidence of corrosion, like from the environment. It looks worse, actually, if you rotate this around and look at it from the other side. And then in the benchtop experiment, we see some evidence of like barrel buckling or deformation. So here there's localized discoloration that would indicate like a temperature rise and subsequent effects as well. So our most recent experiment shows no evidence of scuff marks or internal abrasion that we saw in the previous benchtop experiment using a larger applied deflection. And there's a little bit more about this in the recent webinar. So the dynamic test in CAST is presently in progress at 10 amps test current. Here we dialed this back because we were concerned if there was an effect of weathering, maybe from the elevated chamber temperature or humidity that was present. We may follow up with a second round of CAST experiments at 12 amps. This was the failure current that was observed in the benchtop tests. And then the comparison of these results will be presented at the upcoming PVSC conference. So remember from today, we did see a very significant effect of mechanical actuation. We're using a push-pull mechanical fixture. And then the static samples were failing at the element within the discrete fuses, whereas with perturbation, we were seeing failure at the connection between the fuse and the branch connector, which was observed in field veiled samples. We did not see failure at the fuse element in the field samples. We are concerned about the issues of mechanical wear, and we saw that in our previous benchtop test. And then the occurrence of added corrosion that was observed in some of the field samples. So I'd like to thank folks helping out with DURAMAT. The CAST is a capital intensive effort, so I'm sure there's been some help with equipment and stuff like that. Thank you to our sponsor, and then a reminder to put your questions and comments in the chat feature. Okay, so thanks for your attention.